So for this one, first of all, doing the probability distribution for this game. So the one thing you have to remember about the games is that if the tickets cost a certain amount, you have to figure that into the outcomes for what is won or lost. So we have a $1 ticket cost to start with. And then when we're doing this, we're also looking at the outcomes from the school's point of view. So if we have these tickets that were first prize winners, the ticket holder can redeem them for $5, which means the school is paying out $5 for each one of those tickets. But for each one of those, they already got $1 from the person who bought the ticket. So their net loss on those tickets is a -$4. And then for those tickets, the probability of having one of those tickets was 0.025. So we can go ahead and fill in the probability box. Then for the second prize tickets, those can be redeemed for $2. So the school got $1 per ticket, they're paying out $2. So their net loss was $1. And then the probability for that was 0.0625. And last we had some tickets that weren't worth anything. So for those, each of those, the school's net gain was $1 because the person paid $1 for the ticket in the first place. And to figure out the probability for those, remember for a probability distribution, the probabilities have to add up to 1. So if we add 0.025 and 0.0625, that adds up to 0.0875. So we're going to subtract that from 1. That gives us 0.9125. That way these three values add up to 1. So there's our probability distribution. Then we want to find the mean and standard deviation for this distribution. If you want to do it by hand, then you would multiply each value times its probability, and then you would add up those results. So to do it that way, you'd add another column over here, and you'd have -4 times 0.025, and so on. You'd multiply those and then add them up, and that would give you your mean. Now the only problem with doing it by hand is that it also asks you for the standard deviation. For that, you really need to use your calculator anyway. I'm going to put this probability distribution into my calculator. So I'm doing stat and edit. I have to go clear out the lists I have in here. So I'm putting the x values into L1, and then my probabilities into L2. And then I'm going to use 1-bar stats. So it's the stat button and then calc and then the 1-bar stats. And I have to tell it that I have 2 lists. So where it says list L1 and then for frequency list, I want to tell it L2. So I'm doing second and the 2 button. Okay, so my mean is the x bar, so that's the 0.75. My standard deviation is the sigma x, so that is 0.901. Okay, and then for the expected value, remember that the expected value is the same thing as the mean. So this would be 0.75, or in other words, 75 cents per ticket. Okay, then for number 2, this one is talking about a binomial experiment. So the things that you want to look for are whether it's with or without replacement, whether there are only 2 outcomes or more than 2 outcomes, and whether there are a fixed number of trials. So in this one, since the experiment consists of drawing 10 marbles, that's your number of trials. So the number of trials is 10. So it meets that requirement about having the fixed number of trials. Okay, and then it's selecting from the bag with replacement. So that means that the trials are independent. So that requirement is met. And then it says it's recording the colors of the marbles. So we actually have 3 different colors. So that means that if they're just recording the colors, that means there are 3 possible outcomes for each trial. So that doesn't meet the requirement because it has to be only 2 possible outcomes. So that means that it doesn't meet the requirements of a binomial experiment. So this is another one where it's asking you if it meets the requirements of a binomial distribution. So we want to think about those same things. So first of all, we have a random sample of 12 households selected, and this is selecting from households in the US. So we do have a fixed number of trials, which would be 12, since we're selecting 12 households. And then for the independents, this time we're not selecting with replacement, but if we're looking at all the households in the US, that's a very large population. So that means we can use that 5% rule, which says you can count the trials as being independent if the sample size is less than 5% of the population size. It's definitely going to be less than 5% in this case. So the trials are independent. So that's true. And then we want to look at our outcomes. So what they're asking is about whether the household has a landline or not. So that makes our 2 possible outcomes. So that requirement is met. And then the other one is that the probability of success is the same for each trial. So for this, our probability of success, if 42% of households do have a landline, our probability of success for each time we select one household would be 42%. So it's the same for each one. So that requirement is met also. Okay, so yes, it does meet the requirements. So we need to find the N and the P. So the N is just the number of trials. So the N is 12. And then the P is the probability of success on each trial. So that's 42%. And we usually want to write that as a decimal, so it would be 0.42. And then we want to describe what the variable X would represent. X is the number of successes. If we're counting our P as 42%, that means we're saying that a success is that the household does have a landline. So our X is going to be the number of households with a landline out of the 12. Okay, so then we can do some of these probability problems. And here's where you really have to think about these. If you have something that seems like it looks like a binomial experiment, then you have to think about how to do the probabilities and use the binom PDF or the binom CDF on your calculator. So for example, this one, you might see this and say, well, okay, 6 out of 12 means 50%. That's not what this is, because you're actually doing this as a binomial distribution. So this is saying, find the probability that X is exactly 6, and we have this binomial distribution with N equals 12, P equals 0.42. So on your calculator, you do binom PDF, put in your N, your P, and your X. Okay, so this comes out to be 0.1931. So it's not at all the same as 50%. Okay, then the probability that fewer than 5 have a landline. Remember, if you do have a binomial distribution, then your sample space, so all the possible outcomes is all the possible numbers of successes. So your sample space goes from 0 up to 12 in this one. So it goes from 0 up to your number of trials. So if we want fewer than 5, you have to pay strict attention to whether you're including the number or not. Fewer than 5 means you're not including the 5. So fewer than 5 would include the outcomes 0, 1, 2, 3, and 4. So for this one, you could use the binomial CDF because it automatically goes from 0 up to whatever number you put in for x. So we could do binomial CDF, put in our n, our p, and the top number here, which is the 4. Okay, so this comes out to be 0.3825. Okay, then the probability that at least 6 have a landline. Again, we want to look at this sample space and figure out exactly which of those outcomes would be included in this. At least 6 means it's 6 or more. So this would be everything from 6 up to 12. So we can't use the binomial CDF directly because it automatically goes from 0 up to a number. And we don't really want to find each of these separately and add them all together. So what we can do instead is use the complement. So the complement of this would be everything from 0 up to 5. So it's everything from the sample space that's not already included here. For this one, we could use binomial CDF. We just want to put in 5 for our x. So that's going to give us 0.6111. But then to get the probability for this one, we have to subtract this number from 1. So this is going to be 1 minus 0.6111, which is going to be 0.3889. So that's actually our answer for that question. Okay, then the probability that at least one of the households has a landline, that means that we're going from 1 up to 12. So again, we want to use the complement. If we look at this compared to our sample space up here, the only thing that's missing is 0. So the complement of this is just 0. So for this one, we could use the binomial PDF. And just put in 0 for our x. So that's 0.0014. So to find the probability for this one, we take 1 minus 0.0014, which would give us 0.9986. So that's the answer for that one. Okay, then for the mean and the standard deviation, these ones are both really easy for the binomial distribution. So for the mean, it's NP. For the standard deviation, it's the square root of n times p times 1 minus p. So we already know the n and the p. So for the mean, we're going to have 12 times 0.42. For the standard deviation, we'd have the square root of 12 times 0.42 times 1 minus 0.42. So our mean would be 5.04, our standard deviation is going to be 1.71. Okay, and then last question on this one is, out of the sample of 12 households, how many would you expect to have landlines? The keyword here is expect. That means it's asking for the expected value. That's the same as the mean. So that's 5.04. So you'd expect to have approximately 5 of them with landlines. Okay, these next questions are from chapter 6. So this one's talking about a standard normal distribution. Remember that that means that the mean is 0 and the standard deviation is 1. Okay, so I'm trying to find the probability that z is less than negative 2.7. I'm going to sketch my normal distribution, just put the mean in the middle. And I'm going to put the negative 2.7 down here. And since this is pointing to the left, that means I'm interested in this area to the left. So on my calculator, I'm going to use normal CDF. For my lower bound, since this keeps going down this way, I'm going to use a big negative number like negative 10,000. For my upper bound, it's going to be the negative 2.7. Then my mean is 0 and my standard deviation is 1. So I get 0.0035. Okay, then in this one it's asking for a value of z, and it's giving me an area. So this is the other kind of problem, which means I'm going to use my inverse norm function. So here's my picture. I want to find the z so that the area to the right of it, oops, going this way, is 0.37. So from this number to the right, this area I want to be 0.37. Now the inverse norm on the calculator assumes that you're going from the number to the left. So I need to find the area in this part over here so that I know what to put in my calculator. These two pieces have to add up to 1. So this area over here is 1 minus 0.37, which is 0.63. So on my calculator, I'm going to do inverse norm. I'm putting in my area to the left, which is 0.63. And since we're still talking about z, this is a 0 and a 1. Okay, so that gives me an answer of 0.33. So that's my value of z is 0.33. Okay, here's another one with a normal distribution. This one, it tells you the mean and the standard deviation, so this is not a standard normal distribution. When you use your calculator functions, you're going to have to put these two values in for the mean and the standard deviation. So first it asks what percentage are taller than 22 feet. So here's my picture. My mean is 16 right there. Taller than 22 means greater than 22, so I'm going to put my 22 over here, and that means I'm shading to the right. So I'm going to use my normal CDF. I'm going to put in 22 for my lower bound, a big positive number for my upper bound, and then the 16 for the mean and the 3.4 for the standard deviation. So what I get is 0.0388. So since it asks for a percentage in this one, I'm going to change this to a percentage, which would be 3.88%. So this much percent of the pine trees in the park are taller than 22 feet. Okay, then it wants the probability that a pine tree is between 10 and 15 feet tall. So here's my picture again. And the 10 and the 15 are both on this side of the mean, so I'm going to put those over here. I want it to be between those two, so I'm just going to shade in between those two numbers. Since I'm trying to find the probability, that means I'm using normal CDF. I have my lower and my upper bound already, and then I just have to put in my mean and standard deviation. So when I do this, I get 0.3455. So that's my probability. Okay, then we're trying to find the cutoff height for the tallest 10% of the trees. So this time they're giving us a percentage, which is the same as a probability or an area, and they're asking us to find a height. And especially if it says something about the cutoff, that means that you're going to use inverse norm. So if I want the tallest 10%, that means they're going to be over here. So I want to know what this height would have to be so that this area over here is 10%, or 0.10. Now if I'm using inverse norm, it automatically goes from the number to the left. So I'm going to have to find the area for this part over here. So I'm going to take 1 minus 0.10, which is going to give me 0.9. So I'm going to use 0.9 for my area in the inverse norm function. Okay, so that gives me 20.4. So that means my cutoff value right here is 20.4 feet. Okay, one more from this one. This time we have a random sample of 40 pine trees that are selected. And it's asking about the probability not just for one tree, but for the sample mean height to be less than 14.3 feet. So this time we have to think about the distribution for the sample means. So the mean is the same. So our mean is going to be the 16. But the standard deviation for this, we take our original standard deviation and divide it by the square root of the sample size. So that's going to be our original standard deviation of 3.4 divided by the square root of 40. So we're going to use this for our standard deviation instead of just the 3.4. So we still have our picture, and our picture still has 16 in the middle. We want the probability that the mean height is less than 14.3 feet. So I'm going to put 14.3 over here. Less than that would mean going to the left. So for my normal CDF function, I'm going to put in a large negative number for my lower bound, 14.3 for my upper bound, 16 for my mean, and then I'm going to calculate this to figure out what to put in for my standard deviation. Okay, so this is 0.54. So I'm going to put in 0.54 for my standard deviation. Okay, and this gives me, on the calculator, it gives me this number, and the little e with the -4 at the end means it's in scientific notation. So this is actually 8.2 times 10 to the -4th is what it's giving me on the calculator. Which, to write this in standard notation, I'd move my decimal point 4 places to the left. So that's 0.00082. So that's a very small probability. Okay, so now let's talk about confidence intervals. So first of all, if I were taking this test, because for the critical values from the z distribution, from the normal distribution, they're always the same for the same confidence levels. So these are the 3 kind of standard confidence levels. I would just, before I started the test, I would just have these 3 written down so that I didn't have to go back and try to calculate them every time. So that's why I put this, just have these 3 written down. So this one goes with 90%, this one is for 95, and this one is for 99. Now, if you need to find a critical value for some other level, then what you have to do is find the alpha over 2 and then use your inverse norm function. So the alpha is 100% minus your confidence level. So that's going to be 7%. We want to write this as a decimal, so that's 0.07. Then this tells you to take the alpha and divide it by 2. So we have 0.07 divided by 2, which would be 0.035. Okay, so then what we're doing is we're using inverse norm. This is our area. And since we're talking about z, that means our mean is 0 and our standard deviation is 1. Okay, so this on the calculator comes up to be negative 1.81. For the critical value, you just take off the negative. So the critical value, we would just say is 1.81. This next one asks for a critical value, but this is for a t instead of a z. T's, they change with the sample size. So these ones you can't just have written down a bunch of standard values because there aren't any standard values. So this one you have to calculate it every time. We start the same way though. We look for our alpha and find our alpha over 2. So our alpha is 100% minus 90%, which is 10%. If we write that as a decimal, that's 0.1. Alpha over 2, we take that and divide it by 2, we get 0.05. So this is the area that we're going to put in. And then for our degrees of freedom, this is n-1. Our sample size was 37. So that means our degrees of freedom is 36. Okay, so on the calculator, we're going to do the inverse t function. And then for the area, we're putting in 0.05. For the degrees of freedom, we're putting in the 36. So this value is 1.69. And again, all I'm doing is taking off the negative that came up on the calculator. Okay, so this last one is for critical values for chi-squared. So again, we're finding our alpha. So our alpha is going to be 1% or 0.01. That means alpha over 2 is going to be 0.005. And this was the one that was in the video to find these for the chi-squared. distribution. This is where you use the solver. So I'm doing math and the solver, and I'm going to change this. So I'm putting in my degrees of freedom here. That's n minus 1, so the degrees of freedom is going to be 24. And then I'm going to start out by finding the one for the other side, so it's the 0.005. Okay, so it's giving me for critical value, for one of the critical values is 9.886. And then to find the other one, I just have to go back and change my 0.005 to 1 minus that. So that would be 0.995. So that's why up here it has alpha over 2 and 1 minus alpha over 2. Those are the two values that you put in there. Okay, so this one is 45.56. Or 0.559. Okay, this one, in this one, they're already giving you the confidence interval, and then they're asking you from that to find the point estimate and the margin of error. So just remember that if you have either proportions or means, the point estimate is exactly halfway in between the two ends of the confidence interval. So it's exactly in the middle of the confidence interval. So you can even take the two values, the two limits, and just average them. So just add them up and then divide by 2. So our point estimate for this would be 66%. Then for the margin of error, that's just the distance from the point estimate to either one of the two limits. So if we have our upper limit is 69% and our point estimate was 66%, the difference between those two is 3%. So that's our margin of error. Okay, for this next one, we're actually going to find a confidence interval. So one of the most important things with confidence intervals is to be really careful about reading them and figure out which type of confidence interval it is, because that makes a big difference in which formulas you're going to use. So this one, you're trying to find a confidence interval for a population proportion. So that means we want to use all the formulas that have to do with proportions. So for our margin of error for this, for this one we have our critical value, and then we have the p hat times the 1 minus p hat divided by the sample size. So there's our margin of error formula. Now this one, it wasn't even nice enough to give you the p hat. You have to figure that out too. So if they don't give you a percentage or a proportion for the p hat, you can figure it out by doing the number of successes over the sample size. So in this one, our number of successes was 297. So our p hat is going to be 297 over 400. Which is in decimal 0.7425. Okay, and this one, it wants a 90% confidence interval. To get our critical value, I'm going to go back to those three that we had written down. So for a 90% confidence interval, the critical value is 1.645. That saves me quite a bit of time of having to try and figure that out. Okay, so then I'm putting in 0.7425 1 minus 0.7425, and dividing by 400. Be really careful putting this in your calculator because the 400 has to go under the square root as well as the rest of it. So I'm going to do 1.645 times the square root, and then I'm just putting this stuff in here. And notice how I have one more set of parentheses after the 400. That way my 400 is inside the square root. Okay, so there's my margin of error. I'm going to round that to 3 decimal places, so that's going to be 0.036. Okay, from that, now I can find my confidence interval. So for my confidence interval, I'm going to have my sample proportion minus my margin of error, and then my sample proportion plus my margin of error. So this is going to be that 0.7425 minus the 0.036. This one is the 0.7425 plus the 0.036. So that gives me 0.7065 for that one. And 0.7785 for this one. So there's my confidence interval. Okay, for the next one, it's saying that they're going to do another survey, but they want to know what minimum sample size they need to use. So in this one, there are also 2 different formulas depending on if you have a prior estimate or not. And this one is saying that you do have a prior estimate for p hat. We're going to use the one from the previous survey. So that means that our prior estimate is 0.7425. Okay, so the formula, if you do have a prior estimate, is you take your critical value and square it, and then you have your prior estimate and 1 minus your prior estimate, and that's all over your margin of error squared. So we can plug these things in. Our critical value is 1.645, just like it was up here, since it's a 90% confidence level. So we have that. We're going to plug in 0.7425 for our P star. Okay, and then for the margin of error, it says 3 percentage points. So this is 3%, but you have to change this to a decimal. If you're talking about anything with proportions, you can't use percentages, you have to use decimals. So we want to change that to 0.03 squared. So I come up with 574.9. For minimum sample size problems, you always have to round up to the next whole number, so that's going to round up to 575. So that's my minimum sample size. Okay, now if I'm doing the same thing, but there's no prior estimate for the sample proportion, then my formula, instead of these 2 things here, I just have a 0.25. So this formula is actually a little bit easier. Okay, so this one gives me 751.7. I'm going to round that up to 752. Okay, in this next one, Now I'm finding a confidence interval for a mean. So again, you want to read through the problem and make sure that you know which thing you're trying to find a confidence interval for so that you get the right formula. The formula for the margin of error looks like this. So we're going to have to find our critical value using the inverse t function. The s is the standard deviation. So this is the s, and the n is the sample size. So our sample size is 41. So we have s is 15.4, the n is 41. All right, so let's find our critical value. We want a 95% confidence interval. So that means our alpha is 5%. Alpha over 2 is going to be 0.025 in decimal. And then for our inverse t distribution, we need the degrees of freedom, which is n minus 1. So we'll have 40 degrees of freedom. Okay, so I'm doing inverse t. My area is 0.025. My degrees of freedom is 40. So that gives me negative 2.02. I'm just going to take off the negative. So that means my t alpha over 2 is 2.02. So I'm going to plug these three numbers into this formula. So that gives me 4.9. Okay, so this is my margin of error. For my confidence interval, I want to take my point estimate, which is my sample mean. So I want to take my sample mean minus the margin of error, and then my sample mean plus the margin of error. So that's going to be 193 minus 4.9 and 193 plus 4.9. Which gives me 188.1 and 197.9. So that's my confidence interval. Okay, then with this one, they're planning a new study and they're trying to figure out how many eggs have to be tested. So what this is asking for is a minimum sample size. And kind of keep in mind on these problems, if it doesn't give you a sample size, but it's talking about a confidence level and so on, then it's probably asking you to find the minimum sample size. And since this has to do with a mean, then the formula looks like this. The sigma star is a prior estimate or an estimate for the standard deviation. So in this one, they tell you to use the previous study to estimate the sigma. So in that one, our S was 15.4. So we're going to use 15.4 for our estimate for the standard deviation. This one, it has a Z instead of a T. Since this is 95%, we've got that critical value already. If we go back to our list of critical values, that one is 1.96. And then the E that we want, it says estimate to within 3 milligrams. So that's telling you to use 3 for E. And this one, since we're not talking about proportions, we don't change this to a decimal. This is already the value that we want it to be. So we're just going to use 3 as E. So that means our formula we have the 1.96 here times the 15.4 divided by 3, and then that entire thing gets squared. Okay, so we get 101.2. Again, we're going to round this up. So we're going to round it up to 102. So that's our minimum sample size. Okay, last question is to find a 95% confidence interval for the standard deviation for the chicken eggs. So this time with the standard deviation, we have another different set of formulas. This one, we don't even have the margin of error. We just have this one big complicated formula. So this one we have n minus 1 times s squared over okay, so these two parts of this one are the same in both places. The only difference between these two is that use the two different critical values. So you have to find your two different critical values from chi-squared to get this one started. So we're going to use our original sample size of 41, so that's the n. And let's see, our standard deviation was 15.4, so that's our S. And now we have to find our two critical values. So for this one, we're looking at 95% confidence. That means that our alpha is 5%, or 0.05. The alpha over 2 is going to be 0.025. And our degrees of freedom is n minus 1, so that's going to be 40. Okay, so this is using the solver again. So I'm going to put in 40 for my degrees of freedom here. And then I'm going to do the alpha over 2 first, so I'm going to put 0.025 here. And then don't forget, every time you do this, you have to do the alpha and the enter button to get it to recalculate. Okay, so we get one critical value of 24.43. And then I'm going to do this over. I'm just going to change this number over here to 1 minus alpha over 2. So 1 minus alpha over 2 is 1 minus 0.025, which is going to be 0.975. Recalculating again. So that's 59.34. So these are my critical values. Okay, so now I'm going to plug everything into these two formulas. So I have 41 minus 1 times 15.4 squared. And again, it doesn't really matter which side you do these on, just when you get ready to say what your confidence interval is, just put the smaller of your two results first. So I'm going to put the 24.43 here and calculate that out. 0.7. And then I'm going to do this one again just with a different critical value down there. So I'm using my other critical value, which was 59.34. So for that one, I get 12.6. Okay, so this is actually the smaller one. So when I write my confidence interval, I'm going to write it as, I'm going to put the 12.6 first, and then the 19.7. So there's my confidence interval for the standard deviation. And for these, your sample standard deviation, your point estimate, isn't usually in exactly the middle between these two, but it should be somewhere in between these two. So if you look at our sample standard deviation up here, 15.4, it is in this interval. That's one way that you can know that you got your values correct. If you did something wrong down here, then your interval may be a long ways away from your sample standard deviation, and that way you know that's not right.